Okay, so I will be giving you some guidance on the problems for homework and practice problems as well that I think are helpful. Okay, so for question one, we are given a 2 centimeter diameter galvanized iron pipe with a total length of 50 centimeters. The water bubbles 7.5 centimeters above the pipe exit, meaning 0.3 is the highest point of the water stream. And we need to determine the flow velocity, whether the flow is laminar or turbulent. And then it lets you to continue to solve the rest of the problem. So first for 1.1, it already labeled 0.1 for us, so we just label with 0.2 and 3. And a student made this connection in office hours that U3 is 0 because 0.3 is at the top of the fountain, it's the max height. And he also made the connection that the free jet concept applies because 0.3, the pipe 3 is exposed to air. I cross this out because I can't give you the full equation, but I can show you where to apply this concept. So these are key concepts that we'll be using to solve the parts of the problem. I can add this to the notes I posted. I just added it right now. Okay, and this is from lecture 10, so you'll be needing this formula and that formula, and this is a helpful slide as well. Okay. So the fluid is no longer constrained, it's exposed only to the atmospheric pressure. Okay. Continuing. So once you find U2, you're able to plug it into the Reynolds number and determine the flow, which then allows you to go on to 1.2, where F is already given. So then you'll determine that flow is turbulent from the given F right here. Okay. These are important values and concepts. Okay, so basic things to find for each part. Okay. Well, the rest is in the schematic, but I could underline. Okay. Okay, so this is a guide of how your problems should be, just to organize. So we will use the continuity concept for 1.4, where U1 equals U2. Okay, so let me know if you have any questions. Okay, and then for question 2, there were a lot of questions on some parts. So we have a fan and a 4-sided 4 elbows, and it gives you the loss coefficient in rho and mu, F, the type of flow, and this situation. Okay, so also determine the minor losses, and this time we have to determine the power. So our formula will be not just the Bernoulli application, it'll be more involved, but I already have lecture slides that'll be helpful to refer to. And here's some more notes for 2.3 because that's the hardest part of the problem. It involves more manipulation. Okay, so this is the practice problem I did on Friday's discussion. So we're dealing with the rupture problem. And students were asking what big L is, since we're actually solving for little l, which is the maximum length allowed if the friction factor is 0.022. Okay, so we're trying to investigate what's the maximum length so that rupture doesn't happen. Okay, so points of reference, elevation reference. So Z1 is 0 because that's where the pump is located. That's what we're setting it. The points to be, Z2 is the elevated height that the hose is at. Okay, so that's why this cancels out. And this is 10 for the variables. Okay, so maximum allowable hose length, continuing. P2 is 0 because it's open discharge to the atmosphere. And it's different from the first problem of homework. So I added some reasonings, what's happening, but I didn't post this yet, so I will add this. I just didn't want to overwhelm you. This is just extra notes for reference in case I don't explain it well. Okay, so I can post this and update my notes. So I'm just comparing the free jet flow concept, why this time it's open discharge. So fluid is released freely, but in problem 1 of homework, fluid was pushed upward. That's why it was free jet. Okay. Okay, so it's going up. And this time it's released freely, so the hose is like that, and the problem 1 was just straight up gushing out. Okay. Continuing, so now we calculate velocity using the cross-section area, and we also find for the nozzle outlet velocity. And just to further explain the specific weight, because the student was asking about this variable, so these are the variables hopefully laid out better from the beginning equation that we used for Bernoulli's equation. Okay, using Bernoulli's equation with head loss due to friction, we apply it. Okay, and then find that L is 1,012 feet. Okay, and those are some common questions that I'm just addressing. And so the connected problem to this is now a different type, but it's using the same schematic. So now we are dealing with, so the first 8.4.4 was rupture, and this time we're working with the collapse situation. So if the pressure falls below 10 psi, below the atmospheric pressure, the hose will collapse. And we still have Q as 0.01, but now our friction factor is 0.015, and before our friction factor was 0.022. Okay. So I just listed out the values because this time it's a little different. Okay, so now that we have everything together, we're still calculating the new L, little l. Okay, and then similarly, we still calculate the same things but different application. Okay, let me know if you have any questions. These were the common questions. P2 is negative because the hose collapses at 10 psi, so P2 is negative 10. Okay, and this time Z1 is 3 feet and Z2 is 0 because the hose will collapse. So that's what we're estimating. Okay, so those are the differences. Okay, and then for 8.5.10, we're dealing with crude oil, and still specific gravity, viscosity is given. So we need to determine the discharge pressures and the power supply to the crude oil at the second pumping station. Okay, so listed everything out in the Bernoulli equation and the values, variables. So no elevation change. So Z2 equals Z4. I'll show that right now. It's kind of blurry, so if you can't refer to your textbook. And this is the discharge concept I was talking about for the 8.4.4, I believe. – 8.5.4. Okay. So now we're seeing that concept in action applied. Now we're applying that concept. Okay. Let me know if you have any questions. And this is an important note to make. So it needs to balance out. Okay. Let me know if you have any questions. Thank you.